All right, I think my screen should be shared.
Yes.
Great. Okay, so I'm Colin. I'm head of research at Abacus AI, and I'll be talking about hard problems in enterprise AI. So as we've seen throughout today, AI has revolutionized many industries. There are really exciting applications of AI happening today. And these algorithms are getting increasingly more powerful and more specialized. However, there are still a few hard challenges that we're facing in AI. So now I'll be talking about 3 of these challenges that are still around. And for each of these 3 subject areas, mitigating bias, explainability, and AutoML, I'll talk about the general problem and some of the popular techniques to tackle these problems, as well as some of the research and solutions that we've come up with here at Abacus. All right, so I'll jump right into the first area, which is mitigating bias. So bias in ML is a big problem if it's left unchecked. One of the most famous examples is the Compass assessment, which is a machine learning model that was used by US judges to decide whether to grant prisoners bail or how long to give their sentences. And so this would take in the prior criminal history, as well as some information about the prisoners, like gender, age, and race. And it was found that this model is actually racially biased. So to prisoners with roughly the same criminal history, it would label a Black criminal as more high risk than a white criminal. So obviously this is a very bad problem, and we want to mitigate this bias. There's also bias in computer vision tasks. For example, many facial recognition systems are being deployed today, but a recent study showed that in the USA, the number of false positives for Asian and African Americans is 10 to 100 times higher than for Caucasians. And unfortunately, this has already had negative effects. There is a case in Michigan where a Black man was falsely accused of a crime because of a false positive in this facial recognition system and was detained for 30 hours. There's also bias in natural language processing. Just one example of many is that he as a doctor is more likely to be auto-completed than something like she is a doctor. Okay, and removing this bias is not easy. Your first reaction for some of the tabular problems might be, what if we just remove race from the list of attributes? But bias can often be correlated with other features. For example, race might be correlated with zip code or something, and bias can also sneak in many subtle ways. There's sampling bias. For example, there might be more policing in predominantly Black neighborhoods, leading to more arrests, and also historical biases. For example, certain classes of people were biased against historically, which shows up if we're using historical data sets. And to learn about more of the subtle areas that biases can arise, I recommend this article, Excavating AI, as well as 2 recent talks at prominent machine learning conferences, which are here below, which are available online. Okay, so what do we do about this? So the first step is to come up with what it means for our model to be fair. And in fact, there have been about 30 definitions, at least in the last few years, because once we have a definition, we can start to come up with algorithms to solve this. So I'll just very briefly talk about 2 of the simplest and most popular definitions. Maybe one of the simplest definitions is called statistical parity. And it just says that, going back to the Compass example, the percent of white prisoners who are labeled as low risk must be the same as the percent of Black prisoners who are labeled as low risk. All right, and Another popular definition is equality of opportunity, and this is more concerned with the number of mistakes that the model makes. Okay, so it says the number of true positive rates must be the same. So for example, our model cannot have more false positives or true positives for one group or the other. And we can also relax these definitions to talk about the amount of the amount that our model does not satisfy these definitions. Okay, so now we can talk about algorithms to mitigate this bias. So there are many techniques. Here are 10 of them from the AIF 360 toolkit, which is online. And we can generally think about these approaches as a trichotomy, which depending on when we apply the debiasing routine. For example, there's pre-processing, which are types of algorithms that we apply to our data set before we do any machine learning. Then there's in-processing, which is we replace our ML training routine with some routine that mitigates the bias. For example, we might add a regularization term. And finally, there's post-processing, and this is used when we already have the predictions, so we only have black box access to the model, and we want to run a routine that mitigates the bias at the very end. So now I'm going to talk about some research we've done here at Abacus, and the idea is that this trichotomy was defined a few years ago. But nowadays, it's very common to start with a large pre-trained model and then fine-tune for your specific use case. And as you can see on the left here, these models are getting larger and larger over time. So it's getting much more popular to fine-tune from a pre-trained model. The way that works is we can just import a very large model that was pre-trained on ImageNet. This is easy to do in TensorFlow and PyTorch and other similar libraries. And then we plug in our own data set and fine tune the model for our data set by just retraining the final fully connected layers. However, in our trichotomy, there's not a really good place to debias this fine tuning use case. For pre and in processing methods, we would have to retrain entirely from scratch, which is very time consuming. And post-processing would work, but since it only assumes black box access to the model, we would lose out on a lot of power because we actually have the model in hand. So here at Abacus, we came up with a new family of debiasing algorithms called interprocessing. And this directly targets the fine-tuning use case. So the idea is that we assume that we start with a pre-trained model, and then we can fine tune it while also mitigating the bias. So we've come up with two benchmark algorithms based on random perturbations and layer-wise optimization. And we also have a very powerful algorithm based on generative adversarial networks. So I'll just give a high-level overview of the technique here. So we have our pre-trained model, the model that's seen below, and then we also have a discriminator, and the goal of the discriminator is to directly try to predict the amount of bias of the pre-trained model for a mini batch of data. And so these two are trained or fine-tuned in tandem, and we add the bias term from the discriminator to the loss function of the pre-trained model so that we can directly use gradient descent to minimize the bias. And we showed this is very effective on many different combinations of data sets and fairness definitions. And we also used it to debias certain models trained on the CelebA data set. And we showed that it mitigates the bias while also achieving a high accuracy. Okay, so I'm going to move on to the next topic, but just to wrap up. So bias can show up in many applications. There are many definitions of fairness and 4 different types of debiasing routines. And we actually have all of our code for interprocessing methods open sourced, so you can access it at this link here. Okay, so next I'm going to move on to explainability. And this is actually a bit related to bias, because so the idea is that our model makes a prediction, and we want to know why did our model come up with that prediction. And this is very useful to us. For one thing, it might help us notice that our model is biased. It can also help debug in other ways. And depending on the application, we might even have a legal obligation to understand why our model made a certain choice. If we have financial or governmental applications. And also it can help us find mistakes in our data labels, and also just leads to faster adoption of AI, because a company is more likely to add AI to its services if it knows how it's working. Okay, so and here's just a quick example. We might have this great model that can predict wolves versus huskies very well, but once we look at the explainability tools, we realize that all we did was make a model that can detect snow, and it's not actually good at detecting wolves versus huskies. Okay, and this is especially important for deep learning, because back in the good old days with decision trees and linear models, the ML models were very explainable. For example, a linear model, just by its nature, every single feature has a weight which directly shows how important it was in order to come to that conclusion, in order to come to a certain prediction. However, deep learning, which has really revolutionized many fields, works really well, but it's much more mysterious. We don't really know, at least at face value, we don't know why the model's making its predictions. And also the classification surface is often very, very nonlinear. Okay, so a common method to explain these predictions is feature attribution. And the idea is that, say that we have this model that predicts what disease a person has. So it makes a prediction, this person has the flu, and then it points to 3 features that were important in coming to this conclusion. So now I'll talk about 2 of the most popular techniques for feature attribution, which are LIME and SHAP. Okay, so for LIME, I'll just give for both of these, I'll give a very high level overview, just give you the key intuition. So for LIME, imagine we have this neural network that is distinguishing these 2 classes, the red and the blue class. And we want to understand why it made this prediction for this red X in the middle. And so what we do is we look in the neighborhood right around this point. Okay, so we look at some of its neighboring data points, and we make predictions, and we find that some of them were labeled X's, but some of them were labeled blue circles. So then, since we're just looking around this small neighborhood, we can actually train a linear classifier just on these data points. And since it's a small area, we can get a pretty good decision boundary here. And then, like I described earlier, linear classifiers are actually very strong for explainability, because just by their nature, every feature has a weight that directly corresponds to its importance in making the prediction. All right, so that's the general idea behind LIME. And now I'll talk about another very popular approach, which is called SHAP. And this is a slightly different approach, because we're not going to train a linear classifier, but instead we want to come up with a formula that corresponds to the contribution of each feature to the prediction. So what we can do is borrow a definition from game theory called Shapley values. And the intuition behind this is that, say we want to figure out what features are important in a certain prediction. Well, the first thing we might try is just take every feature and change it a little bit and then see if the prediction changes or if it stays the same. So we can do that for every feature, and we might see some interesting results for some of the features, but it doesn't give us the full story because there are often very intricate relationships and dependencies among these features. So something that's better is to try many different subsets that contain some features and don't contain other features. And this is what's formalized in Shapley values, where we take the sum over all subsets and then look at the difference in the prediction between including a certain feature and excluding that feature. All right, so that's the general idea behind SHAP. And this is also, it takes a long time to compute because the set of all subsets is exponential, but SHAP has some clever ways of getting around this, the computational bottleneck. And this is also a tool that we use at Abacus AI. We use a variant of SHAP that's available if you go to our website. All right, so now I'm going to move on to the third topic, but just to wrap up. So explainability is very important. And I went over two popular techniques, SLIME and SHAP. Okay, so now I'm going to dive into the third hard problem in AI, which is AutoML. So as we've heard throughout today, there are many steps to artificial intelligence. We need to perform data cleaning, hyperparameter tuning. We need to find the best model. And this requires a lot of data scientists and ML engineers, which costs a lot of money. But what if we could just click a button and then do all of this for free? Or we do all of this with just one algorithm. So that's AutoML. And two of the main pillars are hyperparameter optimization and neural architecture search. So in hyperparameter optimization, we want to find the best parameters like learning rate, batch size, dropout. And so it's typically real valued or categorical features. On the other hand, neural architecture search, we want to find the best architecture. And so we need to search over more complex objects, which are typically graphs, as you can see at the bottom of the slide. We're searching over these directed labeled graphs, which correspond to architectures. So I'll talk a little bit about different neural architecture search techniques. And in general, there are three main components. There's the search space. So what architectures are we searching over? Then there's the search algorithm. And then there's the evaluation method. So when we come up with a new candidate architecture, how do we evaluate it? Do we fully train it and report its accuracy? Or do we do something else like partial training or shared weights? Okay, so I'll just give a very brief overview of some of these methods. I'll start with reinforcement learning, which is the first approach that really popularized neural architecture search research. So the high level idea here is that there's a controller RNN, a recurrent neural network, and in every round, it chooses a new architecture, and then we go and train that architecture and pass back its accuracy. And then the controller takes the accuracy and then updates its own weights. So it gets better and better at proposing new architectures. Next, I'll give the high level idea of regularized evolution. So here we maintain a population of neural architectures. And in every round, we subsample the population, and then we look at the best architectures in our subsample, and we mutate these best architectures randomly. So we just change some parts of the architectures. And then at the end of the round, we kill off the oldest architectures. So over time, this will evolve really strong neural architectures. Also, I'll mention darts. So this is also a very popular technique. And the idea here is that we relax NAS to a continuous problem. And the way we do that is that every place where we need to make a discrete decision, like what operation to put on this edge, we just add all possible choices. So we might add pooling or convolution or skip connect, and then we give each of them a weight. So now that they have weights, which are continuous values, now we have a continuous optimization problem. And therefore, we can use something like gradient descent. So the way they set this up in the darts approach is that they did a bi-level optimization problem where they optimized the weights, the parameters, and the hyperparameters at the same time by alternating the gradient steps to update each of these. And they showed that this gets strong performance in evolving a very strong neural network. Okay, so the last technique I'll talk about is Bayesian optimization. And this is a very powerful technique which has been used successfully all throughout AutoML. And the idea is that we start by picking several random architectures and evaluating them. And then we start this iterative process where first we use all of the architectures we've evaluated so far to train a surrogate to try to model the space of architectures with their accuracies. And then we use our model to choose the next architecture to try. And the way we do the second step is with an acquisition function, as you can see on the right. And the reason acquisition functions are important are so that we trade off exploration versus exploitation. So we might use something like expected improvement or upper confidence bounds. Okay, and so now I'll talk about what sort of surrogate we should use. So typically Gaussian processes are very popular, and the idea here is that we model them using deviations that look like Gaussian noise, but at least originally Gaussian processes don't scale well, both in the number of dimensions and in the number of data points. So here at Abacus, we've also looked into using neural networks as our model, and we've shown that these are very successful in modeling the space of neural architectures. And we can also ensemble them to achieve accuracy and uncertainty estimates. And one of the other components that we've looked at, so as you can see on the left, the architectures are represented as graphs, but we need to convert them into a tensor before we pass them into the neural network. And the typical way to do this is by writing down the adjacency matrix and then flattening it and appending the operations and then feeding this into the neural network. However, this can be a very challenging data structure for the neural network to interpret, since all the features are highly dependent on one another. So one approach that we've come up with at Abacus is a new encoding, which we call the path encoding. And so in this encoding, every path from the input to the output is a feature. So for example, in the search space in this picture, there are about 300 total possible paths, and this architecture here has 4 of them. So you can see on the right that we set those 4 features to be 1. And we show that the path encoding, for the path encoding, each feature is much more correlated with the final accuracy, and the features are all much more independent than for the adjacency matrix encoding. So we showed that the path encoding performs better than the adjacency matrix encoding, and even outperforms other techniques such as graph convolutional networks and variational autoencoders. Okay, so I think I'm almost out of time. So to wrap up AutoML, we looked at a few different techniques, and once again, we have code available online if you go to this GitHub link. And also at that link are a few of the papers we've written about AutoML. All right, so that's what I wanted to talk about, these 3 areas of hard problems in enterprise AI. And with that, I think I'll now look and see if there are questions.
Thanks, Colin. Yeah, I think there are questions in the Q&A and also in the chat if you have a few. Remind everyone, if you have questions to speakers, please post to the Q&A. We are going to go through it right now.
All right, so I see a couple of questions about slides. So I can definitely make these slides available. Currently, they're not available, but I can put a link on, I guess I can put it on the Abacus website. Could a bad actor run this process in reverse? Yeah, I guess technically you could reverse this, although I hope that nobody would do that. In fact, there are often government regulations for any like important type of AI application that says the bias must be below this amount. So there are checks to make sure that our models satisfy some of these debiasing definitions. Yeah, some more questions about slides. Where can we get more information on the path encoding? Yeah, so I linked to the GitHub repository, naszilla/naszilla. You can also find it by going to abacus.ai/research, where you can see all of the papers. And the one about the path encoding is a paper called Bananas. So hopefully you can remember this name. All right, now let me look at the Q&A. Actually, these are repeated questions. Oh yeah, and access to Abacus AI trials. So yeah, so if you go on to our website, abacus.ai, we have a free tier. And actually, I see Bindu is here. Maybe
yeah,
Bindu.
I just wanted to like anyway, that was kind of how we wanted to wrap up anyway. So yeah, if any of you want to try Abacus, we do have a free tier, as Colin just mentioned. You can go to our website and just sign up, and we will probably grant you an invite within the day, if not within 48 hours. Any more questions?
I think I went through all of them. Okay. Yeah.
Okay, so do we want to do a couple more raffles maybe, or I don't know if how many were pending, but Bill, do we want to do one at least?
Yes, I think we have one more round of the raffle, right?
Okay.
So we can do it quickly. Okay. Let me quickly share my screen. Okay, this is from the last one. Let me just quickly clean up the list here. And import this one again. Okay, I'm going to spin that. Oh. All right, so if you can see the winners, if you're the winner, take a screenshot and reach out to us. We will get the prize to you.
Okay, thank you everyone for coming. We're very excited to have all of you here, especially the ones who stayed from the beginning to the end. We're going to be doing this on a quarterly basis, so hopefully we'll see you on the next one. And yeah, all of these videos will be available on our YouTube channel, Abacus AI, also on, I guess, the AI Camps channel, so you should be able to access that. And we will also be on Twitter, where we're going to be sharing some of these moments, some of these videos. Our Twitter handle is Abacus AI. Again, thanks for coming. Thank you. Bye.